Okay. All right. So again, yeah, like I mentioned, first of all, like before, as we jump into it here, it's like, thank you for your time. I appreciate it. It was kind of a wacky idea and something we hadn't done before. So I do appreciate that, taking your time out of your day as well. Like I mentioned, I'm John Nelson. I'm the steward of the St. Croix Yacht Club that for 2024, which means I'm in charge of like our membership and content sort of development and creation, having a good time with that. And so again, thank you for joining today. Give you a little background. So before I'll let everybody introduce themselves here as well, but um, this has been a fun project that I've had here as well. As we started this year, we came into the spring, we had really low water, right? And we dealt with a lot of low water last year out on our beaches. So we have two beaches here, one in kind of across the river from the Bayport Power Plant, and the second beach that we go to is down near Afton. So it's just across the river from Afton on the St. Croix River. And so water levels to us are a big deal. And so those graphs that are published, I bet every one of my 250 members has that bookmarked somewhere on their phone, right? And so water levels just drive boating and our enjoyment with the river here as well. And so this year it started off very low, and then we had a lot of rain, and then it pushed that up, into over 80. I think it was 80, almost 83 at some point around the 4th of July or shortly before that, and then came back down. And then actually we just had our second big like beach party, and we had to move it because there was that spike, right? That came up real fast and then has been receding here as well. And so we use this data all the time. Everybody's watching it in the spring, trying to figure out when they can get their boats in. It also drives our big parties. So like these parties for our organization are somewhere between 60 and like 100 boats on the beach as well. And so we want to conduct these events and these parties in a very safe and manner, right? And so when, for example, that past storm really pushed up the river levels, we're using that data probably a week to 2 weeks out, trying to predict like how will our beaches be? Do we have enough capacity? Can we do that safe? And so all of a sudden, we're talking about this data. And in my life, I work for Anderson Windows. I'm a master black belt of Lean Six Sigma. So like data is like at my core, if you guys know at all what that is, and statistical process control and all of that, right? And so it started making me wonder, like, hey, I'm using this graph all the time. Like, where does that come from? Like, who's responsible for some of this data behind the scenes? And how do you guys predict that, right? And so that is the genesis of the conversation today. So with that, do you mind if we just kind of go around and say, introduce yourself?
I'll go first. Yeah, absolutely, because everything you just said is that right at the core of what our mission is. So we want to provide you with the weather information, the water information, so that you can make the best decisions possible, so you can have your events and keep people safe. So that's what our core mission is. So my name is Mike Welvert. I'm the Service Coordination Hydrologist at the North Central River Forecast Center. We're based in Chanhassen, and I'll have a presentation. We're going to show you more about our area of responsibility and some of the duties and responsibilities that we have, and some of the forecasting responsibilities that we have. So that is my core duty. I'm kind of in charge of the outreach and dealing with public interactions such as this. And then I also draw in others from my staff to provide information, which is why we have a couple other people with us. So with that, I'll go maybe to Masha next.
Perfect.
Thanks. Hi, my name is Masha Hoy. I work with Mike in the same building at the River Forecast Center, and I'm the primary forecaster for the basin that includes the St. Croix River from its headwaters down to its confluence of the Mississippi River. And so as not to silo expertise and knowledge at our office, the primary forecaster duty for any given basin does rotate over time, but I've had it for 3 years, and so I'm in the conversation today.
Awesome.
Hey, John. I'm Jake Beitlick. I'm with the National Weather Service Forecast Office in the Twin Cities. I'm the Science and Operations Officer. So you'll see the area that we cover, but we're focused on the weather. And of course, the weather produces the rainfall. So when the rain falls, we hand it over to Mike and Masha. But My job is to make sure that our staff remain up to date on the latest forecasting techniques, messaging, effective messaging, things of that nature. So happy to be here.
Awesome. Super fun. So Mike,
And
did you say you have a presentation?
Yes, I do. One other thing I'll point out is initially in our conversations, you had included Craig Schmidt, who was the service hydrologist for Jake's weather forecast office. He just retired. So right now that position is vacant, which is why Jake's kind of filling in today. So normally you would be talking directly, and we'll talk about this more in our presentation, but you would normally be talking to the weather forecast office, the hydrologist that's associated with them. They'd be your primary contact, and then they would get us involved if need be, and I'll explain why when we get into the presentation. So let me see if I can do the sharing thing and get this working. I got to figure this out. All right. Share. There it is. I'm not super versed in Teams. We don't do as much with Teams, but I'll get it figured out.
Yeah, I live most of my life out of Microsoft Teams, by the way.
Why can I not find it? It's not an available window for me. Why is this?
So did you find?
I found it.
Okay, perfect.
Let's see. Let me know when you can see it.
Yes, I can see it.
Okay, you got it. All right. So if you lose my eyes, that's because I'm looking at a different screen to make sure that I have everything the way I need to have it. So opening slide just has our names and such like that. If you ever need to get in contact with us, you have our emails now through the email that we've been sharing. But we're just going to talk a little bit about weather service products, services, whether it comes from the Weather Forecast Office or the River Forecast Center, and how we work together to provide you with the information that you need. So first of all, for the River Forecast Center, we have a really large area of responsibility. We cover about 350,000 square miles, parts of 9 states and parts of southern Canada. Within that footprint, there are many weather forecast offices around the country, and our footprint overlaps with about 20 of those. How many are there, Jake? 122 weather offices around the country. So we have 20 of them in our service area. So my responsibility is to interact with those, make sure we're providing them with the information that they need so that they can get the information out to their partners. Within that, we have 3 major water drainages that we forecast for. We have the Hudson Bay drainage, which is parts of North Dakota that drains north into Hudson Bay, which includes Souris River that goes through Minot. We have the Red River, the north, which goes through Fargo and Grand Forks. We also have the Rainy River, which is way up north, flowing through Lake of the Woods and such. We have the Great Lakes drainage, so anything that flows into Lake Superior, Lake Michigan, and also Huron, I guess. So anything there. And we also have, of course, the upper Mississippi drainage from the headwaters all the way down to just south of St. Louis. And then we have other river forecast centers that pick up the water from there and do the forecasting further downstream. So very large footprint. Within that, we break it down further into about 33 different primary basins. And each one of those is assigned a primary forecaster in our office. In this case, Masha is the primary for the upper Mississippi, which includes, the headwaters of Mississippi down to about Red Wing, and that includes the St. Croix drainage. So that's why she's joined us today. And beyond that, we break it down even further. We have about 1,225 basins modeled in our computer system that we keep track of every day, at least twice a day, many times more than twice a day, just looking at things and making sure that everything lines up. Because as each basin produces its forecast information, that then is routed downstream to the next part, which goes to the next part, which goes to the next part, and that creates the river forecast as we work our way downstream. Within that area, we have 462 official Weather Service forecast points, but we have information on pretty much any one of those 1,225 basins. So there are forecast points in the St. Croix, and Masha maybe can identify some of those as we move along here if we need to. But a pretty large footprint that keeps us quite busy. Now I'm going to let Jake talk a little bit about what the Weather Forecast Office does and what their responsibility is.
Thanks, Mike. So that light blue area, that shows our forecast area. So that is all the way from the South Dakota border down to I-90 and the Iowa border up to Lake Mille Lacs, Little Falls area. And then we do have 9 counties in Wisconsin also. So we're responsible for issuing updated 7-day forecasts. And then we do all the watches, all the warnings, all the advisories. So when there's severe weather, we'll ramp up staffing. When we have winter storms, we'll ramp up staffing. And that's the area that we cover. And then within that area are also, like Mike said, several rivers, several forecast points where we issue river flood warnings as well.
And then you can also see on the map that there are other, of course, weather offices around the state, Minnesota and Wisconsin and all the surrounding states. So you can kind of see where the responsibilities lie as far as coordination with the local partners. So it's kind of we have a large footprint, and then we help out the smaller footprints so that they can get a little bit more detail. Since most of your questions were kind of river forecast focused, we decided that we would lead the presentation and then Jake could chime in where that was necessary. So I'm going to give just some general overview of what we do at the River Forecast Center. And then at the end, we're going to talk about all those questions that you sent us. And hopefully I'll touch on some of them during all this, but then we can get into more detail with the questions. So our general operational duty is we have the staff that are working every day. We're here every day. We open our shop at about 6 in the morning. We close at 10 at night. If there's serious flooding going on that requires it, we will stay overnight. So we have staffing that's available to work 24/7 if we need to. At Jake's office, their people are there 24/7, 365. So the weather doesn't take any time off. So we have to be around. So there's no vacation for the weather. So for the riverside, we are watching and responsible for creating river forecasts daily. Most of the forecasts that go out to 7 days in our area. We do have some locations where we produce a 14-day forecast and a few where we actually do 28-day forecasts. That supports some of the shipping industry on the Mississippi. We create those daily forecasts. We have contingency forecasts. So if our normal forecast only includes 24 hours or 1 day of future rainfall, and there's a reason for that, maybe I'll talk about it in a second. But we can do scenarios where we can include 2 days, 3 days, 7 days of rainfall, just to get an idea of what the possibilities might be further down the road. So that's some useful information. We produce other short-term probabilistic guidance, like what's the chance we could get to this? And I have a couple graphics later I can show regarding that HEFS that you see on the third bullet there. We also produce long-range forecasts out to 90 days. Those are those spring flood outlooks that you see sometimes. We do produce those all year round. They're of most use in the spring, but we produce them all year round. So I'll show you those. And that's kind of the middle of those 5 graphics there you can see. So some of our operational responsibilities on a daily basis is we're QCing data as it comes in, because obviously if the data is no good, the forecast isn't going to be any good. So data QC is a big part of really both of our operations, making sure that we have the best and accurate information that we can to go through everything. We produce those inputs that go into our forecasting computer models. So we need good temperature data, good precipitation data, good soil temperature data, all the information, snow amounts, everything that we can get that goes into our modeling system. We're coordinating with core partners all the time. Those partners include, for us especially, would be the Corps of Engineers, U.S. Geological Survey. They have most of the gauges that we utilize. But there's also other partners like pollution control agencies, DNR. There's other private entities out there that have gauging that we can get information from. And then, of course, there's all the cooperative observers that we have out there that are taking rainfall measurements. You see those on TV all the time. They'll have a map with all these dots on it, all these reports that come in, and we have access to all that information and even more than probably what you see on TV. So we produce all that stuff so that we can create our river forecasts using our modeling software. We're producing special products to help our partners be able to make decisions as they need to. Do we need sandbags here? Do we need to put up our flood wall? Do we, what do we need to do to keep the people and the infrastructure safe? And then, of course, the river forecasts are kind of our primary vehicle for getting that information out there. We do that in text and also in graphic, and I think you've seen both of those. You alluded to it at the beginning, that you're using it all the time. So that one of those graphics right there is kind of what it looks like. So how do we make a forecast? I'm not going to go into great detail, but I just want to let you know that there's a lot of things that go into it, and maybe touch on just a few of those. So first of all, we need data. I already mentioned that. We get all kinds of different information out there. Of course, we get observational data from observers. We have automated gauges that give us rain data as well as river data. We're getting snow data from not only people measuring snowfall and measuring how much water content that snow is, but we also get remote sensing from satellites. We also have aircraft that go out and measure snow water content via aircraft. We have, of course, radars, many radars out there that we're interpreting to try to decide how much rain has fallen in a certain area. We use the manual observations to corroborate that, to make sure that everything is as accurate as we can get. Satellite data, we have forecasts that are out there for future precipitation. So all these things get wrapped into the forecast. So it's a lot of data that goes in. And if any one or pieces of that are not accurate, that can affect the accuracy of the forecast, of course. So we're doing a lot of data QC, a lot of interpretation of what we're seeing and what's going in to try to make sure that we have the best information available to result in the best forecast available. And
yeah, that's an incredible amount of data to put into a model. That's a really amazing, like, I'd love to see your data stream behind the scene. Like, that's pretty cool, actually.
Yeah, since you're a statistics guy, maybe Jake can plug you in with how much data goes in, because as much data that we have to make a weather forecast or a water forecast, they have even more that goes into the weather forecast. It's crazy amount of data that we have.
Yeah, that's like the 200 level class for next time. But yeah, that's really interesting to see all the different sources of it.
Yeah, it's a lot. So it keeps us busy, and it keeps Jake and his staff busy. So we're constantly doing that. So the process, once we get all that information and feed it into our modeling, we have several different sub models that run within our larger framework that help us to create those things. So the upper left is just kind of real basic water cycle model, where the water falls and it runs off, and it can go soak in, and it can go deep in the soils through percolation effects. It can run off and it can become part of base flow under the ground. It could be there's a lot of different ways that water can go. So we have a model that we use that keeps track of that. I think I have it on the next slide. It's called the Sacramento Soil Moisture Accounting Model, which was developed way back in the 70s, but it still seems to be pretty accurate for us. So that's what our base model is for tracking what happens to the water once it falls on the landscape. Jake's crew is forecasting how much rain's coming in the future, and then we take over and we deal with it once it falls. So there's kind of two parts to that. So we have other models that we're also using within our framework. Keeps track of snow once it falls. What happens with it? Does it melt? Does it sublimate? Does it, what happens to it? Soil moisture, as I mentioned, through that soil moisture accounting model, we use a model called the unit hydrograph, which basically, once rain falls on a landscape, what's the timing? How does that come out of the basin? Does it, and what's the shape of the hydrograph, and what the timing of the water coming through? That can change depending on the intensity of the rainfall, where the rain falls in the basin. So there's a lot of adjustments that can happen in there. We also have reservoirs, and you're well aware of the lock and dam system and how those work. There's some questions about that we'll answer. So there's all these things that go on, and this is just kind of a handful of some of the modeling sub pieces that go into effect. So the bottom two images, so you might see on the left what our model would look like. The model forecast, like that purple and orange line, is what the model is saying might happen there. But then we have the observed, which is those green and black dots, and it looks like that didn't line up too good. But what we determined in this case, this is an example, was that something with the unit hydrograph and how the water came out of this tributary and came out of this tributary, we adjusted the timing of that unit hydrograph, where it fell in the basin. And then we can make adjustments like that to get to look more accurate. So we're doing that every day, twice a day, for those 1,225 basins. So it keeps us kind of busy when it's raining. So here's an example of a couple of the models. The one on the left is our snow model and how it works. So once it's kind of a yes/no type model, where precipitation falls. Was it rain or was it snow? If it's snow, it does this. It goes into a snow pack. Does it start to melt? Does it go through other factors that cause it to sublimate, and how fast does it melt? And so there's all those factors that go in. So we could make some adjustments and tweaks to that. And that's a very, very big part of our efforts from January through April, May, for our biggest floods we usually get on the St. Croix or those spring snowmelt floods. This year we didn't have that because there was no snow. So, but 2 years ago we had like a ton of snow, and we had a big flood. So I think you probably remember that, with all the sandbagging and everything that was going on in your area. So So that's one of the models that we keep track of. And on the right there is that Sacramento soil moisture accounting model. What it does is once the rain falls, several different processes can happen to it. And we have these conceptual buckets where we keep the water. So is it in the upper zone? Is it percolate down to the lower zone? Does it, what parts of it go into base flow? What parts of it run off? There's all those different parameters. So any one of those things, we can, as a hydrologist, go in and look at it, make a tweak or an adjustment. We try not to, because this is more of a long scale type modeling system. If we make an adjustment now that looks good, it might affect things and how it works later. So we got to be really careful in this one, but suffice to say that we have the capability to make those adjustments in that model. And that's true of really any of the sub models that we use in our framework. So some of the forcings that are really primary and key to what we do are obviously the temperature, and also especially the rainfall. So the future rainfall that goes in, and as well as what's already on the ground. So we have part of our team that every day is looking really closely at what's fallen, where it's fallen, what the pattern is, what basins were affected, what basins were not affected, and how that water is going to move through the system. It becomes very important and very key in the timing of everything. And then the temperatures really come into play when we get into the springtime, especially about how that snow is going to behave, how it's going to melt, if it's not going to melt, how fast it's melt, all that kind of thing. And in the summer, it plays in too, as far as how quickly the soils dry out. So temperatures are really key. So those are really our two biggest inputs that we have, other than river data, obviously. But those are the ones that we really pay quite a lot of attention to. We take the precip reports, that upper left image there, it's hard to see, but those are all little rain reports and numbers. We take those, we run them through kind of a Thiessen averaging into like a polygon, and average it out over each of those 1,225 sub basins. And then that's how it looks in that middle image in our modeling system. And then of course the image on the right is the temperatures and how that works. So we're looking at this constantly. It's one of the big things. We have a person assigned to this every day. When they're there, is their main responsibility is to track incoming reports, how the rain fell, how much is coming in the future, all those kinds of things, to keep our model as tweaked and as updated as possible, because we want it ready. So if that rainstorm hits, we can run a scenario and come up with a forecast. We don't want to have to go back and figure this all out. We keep it up to date at all times, if that makes sense. We have, in our footprint, we have 27 different radars in the United States, as well as 8 Canadian radars that we are looking at every day to try to determine what's going on. And we keep track of it hour by hour by hour by hour. So again, we have this one person dedicated to this kind of data QC every day. They're tracking, what fell during the past hour, and they're lining that up with any observations that we get to make sure it's as accurate as possible. Because not only do we need it for our modeling, but we also, this is archived and saved in the US climate record. So if we have any researchers down the road, like 10 years from now, want to do a study, this is viewed as the answer. So we need to make sure this is as accurate and QC'd as much as possible. So that's a really big task that we keep track of every day. Take it pretty serious to get that as right as we can get. Let's see, I lost control, there we go. You can see what precipitation we're using in our model forecasts, and also what we're using from what has fallen on the ground by going to our website. And our website is highlighted there in the red. If you want to jot that one down, you probably have it bookmarked already. But those are the direct links. And I know that's too much to maybe look at right now or write down, but it's available from our webpage to see what kind of rainfall that's fallen has gone into our modeling and what we're using for our future rainfall. And then the images on the bottom are kind of what that looks like when you go to those pages. And we have it by 24-hour period, which is the larger picture, and also by 6-hour sub periods, the smaller insets there. One of your questions asked about partners and gauges and such. The Weather Service does not have any gauges of its own. We're not funded for that. We're supposed to be doing forecasting and monitoring. We have other partners that, especially the U.S. Geological Survey, they have the federal mandate and the funding to actually buy gauges and maintain gauges and do that. So they have something like, I don't know, 12,000 gauges, maybe it's more than that now, across the country that they're monitoring and taking care of all the time. Another big partner for us is the Corps of Engineers. Of course, they have a lot of dams, a lot of lock-in dams across the area. So we're doing a lot of data transfer with them because they run their own models to make sure that they run their dam operations the way they need to, not only for navigation to keep the river in that 9-foot navigation channel so that they can get the barges through, but also in their upstream reservoirs, because they need to keep track of, you know, aquatic vegetation and animals that are living in the water. They've got DNR regulations and everything they've got to account for. So there's all kinds of rules and regulations that they need to keep track of. So there's many, many pieces to the puzzle. Minnesota DNR has a ton of gauges on their own. Minnesota Pollution Control Agency has a bunch of gauges on their own. There's some other entities out there that also do gauge networks, and we try to get plugged into as many of those as we can, because the more data we have to feed that model, the better we are. One of the biggest things that we use, so our modeling is all based on volume. So it's using the flow of water that's coming through the river. It's volume based. But all the observations out there are how high is the river? So like what stage is it? You mentioned 83. In other places, you know, it might be 5 feet or like 12 feet or whatever. What does that mean? So our modeling really needs to have the volume. That's how it accounts for the physical water that's moving through the waterway. So what happens is the U.S. Geological Survey, they're out there, they have all these gauges. They're the primary gauge network. They go out routinely and they're taking measurements. And at, let's say it's at 83 feet, that equates to 12,000 cubic feet per second. That's the volume. So they're making these calculations and they're making a determination. This stage is this volume. So it's a stage discharge relationship. So that's essentially what this curve, this rating curve is. And then they'll go out a month later and they'll do it again. They'll do it a month later, do it again. In low water, they'll go take measurements. In high water, they'll go take measurements. So they're developing this rating curve over time. The more data and the longer the period of record, the better the rating can be. And it's key to us, because if we get a stage that says 83, what does that mean? Okay, it's 12,000 cubic feet per second. We plug that into our model. So we make a conversion. So it's possible there's an error there if the conversion's not right. So that's an error. We run all the magic in our model. It comes out with a volume of, let's say, 14,000 cubic feet per second. We run it through this rating curve again, and it comes out with a stage number. So that's how that forecast gets translated from volume back to stage. So there's another opportunity for the conversion to be wrong if the rating's not right. So we're working with the Corps of Engineers a lot, in the U.S. Geological Survey especially, with all these rating adjustments throughout the year, because they change. Ice affects it. Vegetation in the water affects it. If there's a tree falls in, that can affect it. There's all kinds of things that happen. You mentioned backwater. That's a big one in the St. Croix, because obviously the Mississippi, if it's high or low, changes what's going to happen in the lower St. Croix especially. So that's really big. Maybe Masha can talk more to that as we get to more questions. But so this is one that we're really keeping track of. Between the unit hydrograph and the ratings, we're really keeping track of those things in our modeling to try to keep them as accurate as possible. And if they're not, that's a source of error. So you talked about why things can go awry in a forecast. Those are a couple of them. So, and then we do all our magic and the forecast is perfect, right? So that's
we just, this is what it said. Like, this is where we get all hot and bothered, right? Like, this is what we said. It said this. I'm joking, like, of course, but like, this is the output, right?
And we take it serious. If it's not right, we're always going, well, what went wrong there? We try to fix it so that we learn from our mistakes, or what, where are the sources of error? Can we fix those? Can we prevent those? We're always looking for that. So this is what the images looked like before. We went to the new webpage this year, and now that's kind of what they look like. You probably have noticed that shift and that change. But just a couple more things, then we'll get to your questions, and then you can maybe we can get into more detail on things. But one of the things we introduced here just in the last couple of years is this 10-day probability forecast. This was never available before. It's a new thing in the last couple of years. We call it HEFS, Hydrologic Ensemble Forecast Service. It's a 10-day forecast. It also takes into account the probability of rainfall out to 10 days, because our normal forecast is only 1 day. We do that on purpose because thunderstorms move around. And if we use 5 days of rain and we forecast a thunderstorm in one spot, the amount might be right, but what if it falls 2 counties away? Then you're wrong here because no rain fell, and you're wrong here because you didn't have any rain in. So we kind of limit that by shortening the window. So we're kind of trying to lean into it and edge into the forecast a little bit. So This gives you an opportunity. It takes into account the entire 10 days. So you at least have an idea. Like in this image, you'll see out on, I don't know, 9th or 10th day, you'll see, oh, there's a possibility we could get some rain that takes us up to major flooding level. So it's kind of a tool for our partners and users to look at, to go, oh, maybe I should pay attention to stuff, 8 days from now. That could be, we really have to maybe you've got your big party planned on the 25th here, and you need to maybe think about an alternative plan. So it just gives you another tool, I guess.
Yeah, that's a really interesting tool here as well. I don't think I've seen this before.
And we have it at Stillwater, don't we, Masha? Where do we have it on the St. Croix? I'm trying to remember.
I think it is available at Stillwater, and when you're on the website, there's a tab. Maybe offline we could make sure that the
Sure.
button clicking makes sense, but there's a probabilistic tab, and this would fall under probabilistic products. And so afterwards, if you want, we could make sure that you could access that, or we could
Yeah, I
just send you a
don't
direct link
have
to that.
that. Yeah, I
Awesome.
don't have
Thank
it on
you.
that
Yeah.
much, but
I mean, it's just another tool, right? Like as
Right.
again, it's for us, it's a lot of like risk management here, right?
Yes.
Like we're very big on our safety out there as well. And so even just a probability is worth discussing a lot of times. So that's awesome.
And that's what this tool is for, and that's why we've generated this one and made it available. But I mentioned too, the long range stuff. We do this, and we've been doing this for quite a long time. This is the 90-day outlook, and it's kind of a probability of how high the river might get in the next 3 months. There's a lot of, this is based a lot on past history and what the probability is based off of what's happened in the past, and taking into account what our current condition is. How high is the river now? How wet is the soil now? What are the climatological temperatures expected now? So this is another probabilistic tool, but to have that new one, the more short-term one, that's been a really a good tool for our planners.
Perfect.
So, some other stuff we work on, we obviously data, we're always keeping track of data, new data, changing data, what's available, QC, etc. We're trying to do development stuff so that we can improve and continue to add new things and enhance our services. Other hydrologic activities across our entire 9-state area that we have to keep track of. There's a thing called the National Water Model. You can see that on some of the tabs on those graphics that you're looking at on our webpage. That is not quite as accurate now, but it does allow people to look in areas where we don't have any gauging, we don't have any forecasts. It gives them an idea that they might be expecting some possibility of flooding in their area and how bad it might get. So it's a new tool that's in development. It's been rolled out, but it still has some improvement to do. But at least it's another tool, like we talked about, that gives you an idea of what might be coming. So for future planning, we do stuff with ice jams and ice jam potential, dam breaks if something like that was to happen. We've had a couple recently. Rapidan comes to mind immediately. We're working on a new project called flood inundation mapping, where we're actually going to roll out when the river is expected to get to 83 or whatever feet. This is what's going to be flooded. So we're working on new inundation mapping. That's going to be coming for your area in the next year or two. So we're slowly rolling that out across the country. So that's coming, and we're working on that right now, developing it. There's other research and verification things that we're doing. So there's a lot of things going on. So is there any questions, or do you want to just dive right into the questions that you sent to us?
Yeah, no, I mean, we could probably, I'm sure if we jump into the questions, it'll spark some extra questions here as well. Yeah, on that one.
And I think
I
touched on some of this stuff in my overview here.
Yeah, so that first one, the models,
algorithms,
algorithms, it's all about, those first two questions are absolutely, I think that's what you've been covering here as well.
Yeah.
I think that's a lot of what people were asking about as well.
Okay, cool. So hopefully if they view this, they'll get some of the answers from that. Masha, you got your hand up before we go too much further.
Yep, just before we get into the next topics, I just checked in that same webpage where you're looking at the hydrograph for Stillwater that has our one deterministic forecast. If you scroll down, that's where several of the probabilistic tools that Mike showed will be on that same webpage.
Perfect.
Yes, and I also just wanted to follow up about flood inundation mapping. So Mike said that that's in development, and just going to make a plug here. It sounds like if you have 250 members and some of them are excited about rivers or spending a lot of the time along rivers, it's helpful to have anyone who's willing to spot report, like say there's a flood going on, and to report this road is closed, or the website says that this bridge should be closed, but it's working just fine right now. So just verifying what kinds of flood impacts there are along the river. Anyone can participate, and it's always a huge help, and it helps us improve our products.
Perfect.
All right, so like you said, the first couple of questions have kind of been answered.
Yeah.
Update frequency, I didn't really touch on that too much. We are staffed 6 a.m. to 10 p.m. So it's mandated that we're going through every one of those 1,225 basins twice a day. So we're going through it in the morning hours when we get all the fresh precipitation data from all our cooperative observers. And then we go through it again in the evening. So anywhere between 5 p.m. and 8 p.m., we're going through all that stuff again. So it's updated at least twice a day. During a flood, it's going to be more frequently than that.
Yeah, so this actually is like one of the questions that it's funny. So if you leave a bunch of people to their own, their own observations, they start to come up with hypotheses, right? So it appears that the actuals, the river levels themselves, that's on the gauge data, right? And it must be pulling in pretty frequently. The forecast itself is twice a day. We've noticed that as well, once in the morning and once in the evening.
Yep, that's correct.
That's perfect. That was actually one of the things that just out of this past couple of weeks, like I mentioned, we actually moved one of our parties because the water was coming up, and we were like, I think we're gonna wait till like the morning forecast. And so you basically have validated exactly what we thought was going on. So that's good. That's awesome.
Good. Yeah. Yeah. So during a flood, if it's going to be above the flood stage level, we'll probably update it. I mean, at a minimum twice a day, but it could be, in the afternoon, we could do another update. And if things are rising or falling more quickly than we expect, we might do another update. So it could be, more frequently than that twice a day.
Yeah.
The data itself is coming in like constantly. As new data arrives in our system, it gets populated to the webpage. When we moved to this new system that now has the new graphics, it used to take 20 minutes to an hour for the data to update. Now the data is updating much more quickly. It's up there within 5 minutes of us receiving it. So it's a new system, a little bit more modern. So that's the frequency side of things. Historical data, we are using the historical data. So the longer that a gauge has been in operation, we're using that in our calibration efforts because we want to know, what's happened in the past versus this rainfall. And we're kind of comparing that to what's going on, in the recent years. Has there been some sort of change in the basin? Have we had a scour where the river's now deeper than it used to be? Have we had sedimentation? That's more likely to cause an issue. So we're doing calibration, and not as frequently as we'd like to do, but we are making tweaks. So the historical data is definitely used, and especially in that longer range stuff, we're using that as kind of what's happened in the past to calibrate what can happen in the future. So does that answer that question for you?
Yeah, I think these two this one and the bottom one as well, I think really revolved around I think people are trying to understand, you were talking a little bit, I think you called it ratings before, the conversion of the height to the volumetric type situation, right? And that constant data piece of it. I think that was some of what these questions were revolved around. I think the other half of this is, I think people were genuinely sort of curious if you have noticed, have the floods been more pronounced? Are they more frequent? There was some conversation in the last couple of years around, I think there was some work on locking dams further south that they were, we talked that somebody was mentioning about retaining more water in the upper pools. I think a lot of this was just that historical data and these weather patterns, I guess, in a macro scale. Are you seeing more prolonged floods, higher floods, lower water levels? What kind of things have you seen trends recently, and are they real or not?
The research has been showing that precipitation rate has definitely gone up. So the storms are more efficient. When it does rain, it tends to rain harder. The amounts are higher. And they're attributing a lot of that to the climate change aspect. And you guys chime in if I say anything funny or you want to add to it. So there are some researchers out there that have definitely proven that climate change is having an impact into the frequency of rainfall, the amounts of rainfall, how fast it's falling, its rate. So there's some of that. And with that, we're seeing more rapid response in rivers, higher crests, things like that. But there are other things in play, like there's a lot more drain tile networks out there than there used to be. So when the water does fall in the landscape, it gets to the river a lot faster because no one wants it flooding their field. They want it out of there. So what does that do for people downstream? They're getting the water a lot faster. There's people building levees, which never used to be there before. Floodplains are there for a reason, for that water to slow down and spread out. So more levees are built, the faster the water moves through, the more urbanization there is, the more quickly the water gets into the riverways. So there's a lot of changes that have happened on the landscape in addition to the actual climate itself that are attributing to higher forecasts.
Yeah, that's interesting about the drain tile. You could, I live in Stillwater. You can see there's what do they call it in something ponds in
Retention ponds.
basically retention ponds, like everywhere now. And we see like, how fast it goes up and down. I mean, we're putting very large boats like on the beach, which, by the way, that's sort of a uniqueness of our boating in our area here as well. But over a weekend, we can see the water go up and down. It feels like 6 inches. I don't know if it ever is like that, but that makes big difference between like, hey, the water's coming up. We got to be watching the boats. We got to make sure they're connected to land, so they're not breaking loose, or vice versa. If it's dropping real rapidly as well, we're watching that, hey, we got to back off our boats off the beach a little bit more. So, the rate in which it goes up and down is also something we constantly are watching.
Yep.
Yep.
Masha, go ahead. I see your hand.
Sure. I just wanted to add that there's a couple of resources that are great for this that I'm happy to share with you after. Some of the things that Mike was saying about findings about rainfall rates becoming more intense is documented really well in a white paper by the Minnesota Board of Water and Soil Resources that I would be happy to share. It talks about the climate trends in this area, including seasonality. So it's not across the year ubiquitous, the direction of change that precipitation patterns have. There's also really neat tools from the NCEI, the National Center for Environmental Information, where you could visualize how patterns of wetness and dryness you could select your county or the state, have changed over time. Because while there are long-term changes in climate that are measurable, in addition to land use changes, like Mike mentioned, there is also just natural variations. There's periods of more wet and periods of more dry climate that kind of happen at a smaller, noisy scale compared to overall changes in climate. And so you could visualize those for your area, and they're really helpful for seeing what's true. It feels like it's more wet these days. Is that really happening?
Right, right.
Yeah.
That's awesome. And boy, you guys love your acronyms, don't you? Like there are a lot of acronyms. I mean, it makes us seem like pretty minor at Anderson here. So
yeah. We like to joke that NOAA is the National Organization for the Advancement of Acronyms.
That's actually pretty great.
And now it's recorded for all posterity. So
yeah, give everybody a good laugh. Yes. We had some more questions too, didn't we?
Absolutely. I'm going to the next slide if I can find where my mouse went. There it is. Whoops, I went too far. You had asked about error margins. What's the margin of error in our forecasts, and how do we talk about that and the uncertainty? So we're moving toward more probabilistic forecasting. Right now, our forecast is this is the answer. That's what we put out. But we're moving in the next year or two, probably more like two, to put out, even in our daily forecasts, some range of possibility. Think of the hurricane forecast when it's landing in Florida. They have this cone you see. Expect to see more of that kind of thing coming from us in the future years, as we understand there are errors that creep in, and we're not, we can't predict it down to the inch like we try to do right now. There is definitely a range in there. So, and we understand that. So we're working toward more probabilistic tools in the future. But so we understand that, and that we are working toward that. Margin of error, it depends on the situation. If we're expecting a big thunderstorm complex that's going to drop 5 inches of rain, it depends on where that falls. So I mentioned that earlier. If it falls in this county, this is the response we might get. If it falls in this county, this is the response we might get. So we still struggle with the actual placement and amounts, and that can really impact the forecast itself, the timing, the amount of volume that's actually coming through the system. So there's a lot of potential errors that are in there. So we're hoping that with these probabilistic products, it tends to smooth some of that out so that we can get a little closer to the right answer. So that's what we're hoping for right now. We'd like to say that we're accurate within an inch or two, but is that true? I don't know. That's for you to decide, I guess.
Yeah, I would say generally it's pretty accurate, right? Like we might, but it's those it's really these one-off storms that, can create like, I think I think forecast to be I might have this wrong, like 83.3, during our party, and it came out as like 81 or maybe something like that and some change. I might have that off just a little bit, but that's why I think we were just trying to understand the margin of error there as well. And it obviously increases with these one-time sort of rain events as well. For us, that's, the difference between having a party and not, right? And now it's all first world problems. I understand that, but too as well, but it helps us just make better decisions.
Yeah. And then that kind of thing could be a lot of factors. The biggest ones usually is that amount and placement of the rain and how it routes through from upstream. But like you mentioned in one of your questions, the backwater from the Mississippi does impact all the way up to Stillwater. So there are factors that can go in why things would change. But usually when you see a change like that, 83.2, and then it came in at 81.5 instead, that's usually got to do sort of timing or amount of rainfall that was in the forecast. Masha, do you have more to add to that?
Yeah, and I could talk about the backwater at Stillwater too. Yeah, maybe I'll get into that. So the backwater at Stillwater can be challenging. One needs to interpret how much of an effect it even has. So that's compared to we're comparing how much flow is coming out of the St. Croix River compared to the Mississippi River. And depending, if the Mississippi River is high and the St. Croix is low, there's likely to be a backwater effect. But when you're getting to having similar flows out of the two rivers, it gets a little trickier. And the way that we forecast the crests when they're backwater affected at Stillwater is using a lookup table based on the stage at Prescott and flow at Prescott. So like Mike was showing, there's these rating curves that we have, which establish the relationship between the height of water in a river and what the flow is. And those ratings, that relationship, mathematical relationship, tends to fall apart if there is a backwater effect, in which case the rating loops, and you could have multiple flow values for a given stage depending on whether there's backwater or not. And so we have to digress from that strategy and use these lookup tables based on historical relationships between the Mississippi River and the St. Croix River.
Oh, yeah.
So there it gets a little more complicated. So our forecasts are to the 10th of a foot, so we can only forecast at 10th of a foot increments, and we try to be within a couple tenths of a foot. But if there are errors, some of them can be introduced by that backwater effect. Some of them can be introduced, like Mike said, by the placement of precipitation forecast. If it moves, say it moves higher into a basin, it'll just take longer to reach that particular gauge. And then also, especially when there's backwater, another part of the model that we have is routing. So but beyond when water falls in a landscape, how quick does it get to the gauge? Once water's already in the river, how quickly does it move from that river to the next gauge downstream? So the way that water is routed also depends on the if there's backwater and other conditions going on in the river at that time. So those are things that can introduce error to the forecast too. And we are always shooting to be within a couple tenths of a foot.
Yeah, that's like super interesting. And, it's observing this over the years as well. It appears that hey, if we get like a great big rainstorm, let's say in that northwestern Wisconsin part, right up by the Namakagon and all, it eventually hits down here, right? Like it seems like that affects our river levels a lot more than like if a storm hits, let's say Prescott, right? Just because it drains down through the river then at that point.
That's a really good point. And so we model a local flow. So the flow, the rain that's landing on the basin specific to that gauge, and then showing up at the basin. That's usually pretty quick, in addition to the flows routed from upstream. And there are some events where it could be a really intense rain near that gauge, and the local flow is the driver, but a lot of the time it's routed flow that's a driver. And on the St. Croix River, it's a little simpler, but you could imagine on the Mississippi River where there's various tributaries coming in and they're
Yeah.
contributing to different effects on a crest. And if they coincide, it'll magnify that crest. So that's a really big part of our job, is understanding the timing of routing from different upstream areas to a particular gauge.
Yeah, it's fun. Like, I'm very, very focused as I'm sitting here, like looking at the St. Croix out the back window here. I'm very, very focused on that. But like, really, the Mississippi, like being such a, like, that's like where the, true like money is at, right? Like you got all these different, like, coming together and navigation and commercial traffic and stuff too. It's a lot.
Mhm. May I speak to navigation? Mike addressed this to some extent, talking about how we get forecasts from the Corps, but I don't know if this is going to be in future questions, and if I'm skipping ahead, I'm sorry, but I remember that you had questions about how we talk to the Army Corps of Engineers about how locks and dams are regulated, and how do those impact our forecasts at all? And I could tell you this is our process every day, and it's what I did this morning. The St. Paul Army Corps of Engineers district every morning sends their orders, the same that they send to their gate operators. So this morning, for instance, I knew at Lock and Dam 2, they were going to close gates, cut flows, at Lock and Dam 3, hold steady. And I do put that into my forecast, so I know specifically what their targets are. We also know for every lock and dam and reservoir what the target bands are, so we know at any given point of the year where are they trying to keep those locks and dams. So in addition to seeing their forecasts, we can also verify what we believe is likely to happen based on their targets, elevations for those pools. And then it's iterative, because like we're using their orders and their forecasts for what they're going to do at the locks and dams, they're looking at our forecasts for inflows, how the pool is likely to behave based on certain outflows, and adjusting how they manage their gates. So it's this iterative process, and every day us and the Army Corps of Engineers are sending that data back and forth, and we're working together to develop what the forecast ends up being for the river and how the locks and dams end up being managed.
Yeah, that's very interesting. I think that was definitely a question on, I think, at the next page there, Mike, as well. But yeah, that's very cool as well. That's good to know.
Yeah, the shipping industry is really the reason that the lock and dams exist. People think that it's a dam, so they're controlling the flow and they're causing floods, blah, blah, blah. That's 100% false, because those dams exist for one reason, and that's to keep the stair step of the river at a level where the boats can move. That's the only reason they're there. When the water gets high, they pull the gates out of the water. They have no control once we get to flood stage. So people think, well, the dams are causing the flood. They have zero impact in the flood. So that's one misnomer that's out there. But yeah, you talked about go ahead.
I was just going to say, they also can't inadvertently cause a flood. There's really not a lot of storage there. It's not like a water supply reservoir or something, or hydropower reservoir. Like Mike said, they're really just making sure that navigation can happen.
Because the river is kind of set up, the way they manage it is like a stair step. So the boat goes through a lock, it goes up, and it moves across a virtually flat stair. And then it gets to the next dam, it goes up, and it gets to the next dam, goes up. So it's really a stair step if you look at it. There's a gentle slope there, obviously, because river water flows downhill, but it's generally a stair step process. So they don't have any impact in the flooding. So Masha alluded to it with the integration with other agencies. We're in constant coordination with the Corps of Engineers. Like she said, it's an iterative process. They send us what they expect to happen. We send them our flows and what we expect to happen. They put that back in their model. They do other adjustments, and we go back and forth 2 to 3 to 6 times a day with that information. The data from the U.S. Geological Survey, if they go out and do a measurement, this stage is this volume, they make an update to their system, it gets populated into our database within hours. So we're getting that information all the time so that we always have as much new, fresh information that we can get. So we're doing a lot of coordination with these offices. We have Slack. I don't know if you're familiar with the Slack chat vehicle. We have that with all of our partner agencies, and we're just trading information, not only behind the scenes, but we're chatting. Oh, what are we going to do? This dam, we're going to open up these gates and cause this much more flow. Okay, so we plug that into our model. So all this stuff's going on all the time. So it's a constant process. Lots of interaction, to answer your question. Feedback, any feedback that we get from groups like yours, The first line of contact is the local office where Jake is at. You would have talked to Craig, but now he's gone. So you would reach out first to the hydrologist at the local office. And if there's an answer that they can't find for you, then they'll, touch base with us and we'll figure it out. And that we do that for people all across the whole upper Midwest and really across the whole country, local office versus our larger regional office that we are. So that question, and then there was a few more. These are the ones you had at the end that came from your members. Interested to know
a lot of these are what we're talking about.
Yeah, so how privy are we to what the U.S. Corps of Engineers is doing? And we just talked about that. We are talking with them all the time. So we are very privy to what they've got going on. Not only locks and dams, but their projects way up, Leech Lake and Federal Dam and all the dams way up there. You talked about how in the last couple of years we've had such low water. They actually were maintaining and keeping those lakes way up there higher, knowing that as we got to late summer, the river was really going to fall. We needed water from somewhere. So they were holding on to water as long as they could to stay within their regulatory bands that they have to. They were holding on to that water as long as they could, and then they'd release it later to keep the river from getting too low. Because obviously we want to make sure the barges can move. We want to make sure, all that stuff. So, yeah, that would be one question. Does that answer that question, do you think?
It does. I think so. Yep.
How much of the level determined by what happens upstream versus determined by the Mississippi pool level? Yeah, Masha alluded to that a little bit. It all depends on where the rain falls and how it all interacts that way, but depends on which river is the driver, she said. Yeah. This is a question, the third one's a question we get from time to time, but we really don't have a way to monitor that. The average speed of the current in the St. Croix versus the Mississippi. And go ahead, Masha. You look like you want to say something.
I was trying to check really quick while you were reading out this question. I don't know that I can that quickly, but the USGS, when they take the measurements that are used for the rating curve development, they're also measuring flow and they publish that. So on the USGS website, it's possible that you'll find velocity, and obviously the velocity in each of the two rivers varies based on what the flow is at the time. But if you wanted to, out of curiosity, compare for a given flow what the velocity is in the St. Croix River and the Mississippi River, you could find that on the USGS website if you look at field measurements and find a column for velocity for the gauge you're interested in.
For all the data like geek members that we have out there as well, right?
Yeah.
And then of course that, how accurate is that? Because in the center part of the channel, maybe it's moving faster, and on the shore there's back eddies and it's moving slower. So there's all kinds of caveats to that too. So, but you said average speed. So that's always a hard one because when the river's higher, it's moving faster. Just gravity works, but it's lower, it tends to move slower. So there's a lot of factors that can come into it. So, but that's not something that we regularly monitor unless something comes up like let's say there's an oil spill or some sort of other hazmat that goes into the river. Then we get asked that question a lot. So how much the locks and dams on the Mississippi and St. Croix, and how they do the levels. So the locks and dams, I mentioned this already, they exist strictly for navigation of the barge industry and allowing, for that 9-foot navigation channel. And what happens on the St. Croix, I think, is kind of ancillary to what's going on the main stem. So I don't say it's directly done to do anything in the St. Croix. Do you know of anything, Masha, that would be directly done?
Well, I think you actually explained it earlier, which is that when the Mississippi River is actually high, the locks and dams don't have any control. So they're not actually having any impact on the river. The gates are pulled and the river is what we call run of river, just flowing naturally. And high flow conditions on the Mississippi River are the ones that would have an impact on the St. Croix River. So during the conditions when the St. Croix is affected by the Mississippi River, the locks and dams are usually not even a player.
Okay. Yeah, that makes sense as well. And then I think the other flip side of that was, so if they're trying to retain water to hold like their flow rates or whatever, like later in the summer, would that like, is there, because I think the other end of that question, and maybe I'm tripping over my words, is they need to keep that navigable, like that channel at a certain depth, right? And that flow at a certain level. And so there is a point where Like if it hits too low, they're holding it steady at that point, correct? Lower to keep that flow.
But it's a balancing act because
It's a
if let's
balancing
say
act.
let's say the water is getting too low by Hastings, so they close the gates at Dam 2 to make
Yep.
sure the water doesn't get too low. Well, then what happens below the dam? That water gets lower and lower.
Lower,
So
lower, yeah.
so they can't like totally shut it off because it really becomes kind of a balancing act. They gotta keep it as uniform as possible because if they shut one dam off to make it good here,
They'll starve.
killing everybody else downstream. Yeah. So
Yeah.
Yeah.
it's really a balancing
There-
act. And there's districts in St. Paul, there's districts in Rock Island and St. Louis, and they're doing all the coordination all up and down the Mississippi, all the way down to New Orleans, really.
And also, like you said, when they're trying to store water for the summer, in the locks and dams on the Mississippi River, it's not a lot of storage that you could use for supplementing low flows or anything like that. If anything, we're really just relying on water falling in tributaries to the Mississippi River, hopefully throughout the year. But like the headwater reservoirs, not that those are a huge source of storage either, but the same U.S. Army Corps district, St. Paul district, manages the 6 headwater reservoirs to the Mississippi as the locks and dams. And so in a way, they could build up their pools in those reservoirs and supplement a little bit what the water in the Mississippi River is during low flows. But at the locks and dams, they're really not like the kinds of reservoirs where they could be storing water for use to supplement low flow conditions. There's not
Perfect.
that kind of capacity.
Yeah. Yeah. Interesting.
So I think, and then the last thing is this example that you threw at me about what we see here in this forecast is an example of why we want to understand the process. So this is actually a good image to explain a couple of things. So when you sent me this, if you look at the timestamp, this was in the morning. So this is like 9 a.m. on a Thursday, the 8th of August. So if you look at the bottom timestamp, it's hard to see it here. Yeah, right. At the very bottom, it says forecast issued, and it says 7:54 p.m. on the 7th. So this forecast is 14 hours old. So that's number one, probably why there's such a difference between the observed value and the forecast value. It's an old forecast. So then we talked about all the things that could go wrong, which is why the crest came in lower than what we were forecasting. Is it a timing thing? Did the rain not fall as much as what we were expecting? So there's a lot of factors that could go into this. This is kind of a common thing. When you look in the morning, be sure to check that the forecast, when it was issued, because in this particular case, it's just an old forecast from the evening before. And we've got a lot of new data since then. And I think when I looked at this, I went, oh yeah, that doesn't look so good. I looked at it and it showed the forecast actually updated by the time I read your email. So it literally came out like 10 minutes after you sent it. So it's just one of those deals. Was there anything else, Masha?
I didn't have anything to say about this forecast specifically. I think you described well that this is a matter of, when the forecast came out and that something could have changed overnight from when it was issued. Like say there was an intense rainfall meant to happen in the, up to 7 a.m. hour and it moved somewhere else. So that could be a big driver. But it also reminded me that I wanted to make one clarification about something that we talked about earlier so that when we end the call, there isn't confusion afterwards. We talked about how flood forecasts are updated at a minimum 2 times a day, so in the morning and in the evening. And that's true for any location that has a forecast that's above this action stage that you see yellow on that hydrograph. So we're giving a heads up that it's possible that it could reach just under minor flood or exceed into the flood thresholds. There are also some locations that have routine morning forecasts. So Stillwater is one of these. And so when there's no flood, there's still a forecast issued for Stillwater. And then there are some locations that routinely have forecasts in the morning and evening, even if there is no flood condition. Stillwater is not a routine forecast point in the evening. St. Paul is. I think that may be the nearest location. So if you see some locations on the website updating and not others, it's based on where we have forecast services set up to be routine in the morning and evening, or only during flood condition or some combination. So
yeah, that's a really great point out. So yeah, thank you.
Yeah, you're welcome.
Awesome.
Yeah, thanks for that distinction. I forgot to mention that, so thank you. Jake, you got something, bud?
Yeah. So with regards to this hydrograph here, clearly Mike and Masha are the experts when it comes to the river forecasting side of things. But as a user of their information all the time, I just wanted to stress a couple points, and that is the 24-hour QPF. So the fact that we don't, if there's in this case, rain coming on Monday or Tuesday of the following week, it won't be captured in there. So just to keep that in mind. And then also that probabilistic data is really where we're going to be going, so that you can not have, a deterministic forecast like this of just a single number to the nearest tenth of a foot, 4 or 5 days out. So I just want to hit those points home so that people who do look at these hydrographs can keep that in mind just going forward.
Thanks, Jake.
Yeah, that makes sense too.
Whoops, I think that's what I had, John. So
Yeah, well, like, first of all, thank you so much for this as well. This was like extremely helpful for our, I'm sure our members will definitely, like, this is something we've been talking about wanting to do anyway. So I'm so glad it sort of worked out. Like, thank you.
yeah, if you have any questions down the road, you can reach out to us, primarily the weather office first, but then you can come to us if you need to as well. So we're happy to help.
Yeah, we'll do. Thank again, Mike, Jake, and Masha. Thank you so much for your time. I appreciate it.
Yeah, thanks for your interest.
Thanks.
You're welcome.
Thanks, John.
Thanks. Bye now.